Hi guys, this is part 2 of the video of polar form of complex numbers. Hopefully you're good at finding that polar form of complex numbers, because today we are going to be multiplying, dividing, taking them to a power, taking the square root of those complex numbers. Okay. Now in order to do this, we're going to have to use what this Abraham Demoivre came up with. Obviously he is French. And he came up with all these formulas for working with products, quotients, powers, and roots of complex numbers. When he came up with these formulas, it made it so that you didn't have to be a brainiac in order to figure out how to do this. He made these formulas so that you and me can come up with it, because you know that we need those simpler methods in order to come up with it. First up, let's talk about the product of two complex numbers. So they're going to give me two complex numbers, Z1 and Z2, right? And they're going to write them out long ways like this, or they might use that R cis theta idea. Okay, so then the product of these two is going to be, what you can do is you're going to take R1, and you're going to multiply it by R2. Good start, right? And then you're going to take your two thetas, and you're going to add them up after the cosine. And again, we're going to have the same, oops, that's a 0. We're going to have the same thing after each cosine and sine. That angle should stay the same. So, kind of weird on this. We keep the multiplication right here up front, but then it changes to addition when we're dealing with the angles. If we were in class, I'd be able to show you better where this formula comes from. I'm afraid on this video it's just going to make it longer and more confusing than it needs to be. Okay, so let's try this. I want to find Z1 and Z2. Oh, someone gave me degrees. Oh man, we'll work with it. I had trouble with the subscripts on these for some reason. So here's Z1 and Z2. I'm wanting to find the product of these. So that last slide, something good for a note card. We're able to come back to school, or if you're taking this next assessment at home, having that note card right there with all these formulas on it, we still have a long way to go on these formulas. So in order to do Z1 times Z2, let me kind of write out what's going on in my head. I'm going to take 4 times 2, right? I'm taking the R's that are camped out in front right here, okay? And notice that it leaves the polar form pretty well. All right, I've got the 80 degrees, I got the 145 degrees, and I do the same thing. I'm just going to put an I sign, and I'm going to have 80 degrees, got the degree symbol, you notice, and then 145 degrees. Unfortunately, I'm not going to leave my answer like that. Nice if I could. I'm going to want you to do 4 times 2. And I'm going to want you to do 80 plus 145. So thank you, Abraham Demoivre. That made it so it was much easier on that. Okay. I'll let you practice that here in a minute on your own, where we can match answers. But before we do, I want to go ahead and talk about the quotient of 2. Okay, now this one kind of matters, because this is going to be Z1 divided by Z2. In order to get that quotient, what I'm going to do is I'm going to take my R's, I'm going to divide them, same order that I had there, 1 over 2. And then I think you can kind of imagine what's going to happen with these angles. I'm just going to take my angles and subtract them. There's still a plus sign right there. It's kind of a staple no matter what you're using. And that would be the formula for it. Not just a whole lot different, is it? So great note card information right there. So let's just plug everything in. I'm just going to leave that from the last slide. Let's just plug everything in to see what happens on this. So I've got my Z1, I got my Z2. I'll call this Z1, call this one Z2. And so in this case, Z1 divided by Z2. That's what this one should be on the last one. I'm doing all these in one take, so Sorry about that. I'm not going to go back and redo a whole video because of that small error. Maybe I'll have another one in a minute. I'll have to go back and redo it. All right, so Z1 divided by Z2. I'm going to take my two R's, I'm going to divide them. So I have 2 and 4, so that's going to give me 2 fourths out in front. And again, a lot of you are going to be doing this in one step, and that's great. I would be as well. I'm just going to show you, at least for this video right here, what we need to do. And so that's going to be plus I sine 213 degrees minus 33. And then we simplify that. So 2 divided by 4, we're going to call that 1/2. And then we're going to call 213 minus 33, call that 180. Put pi if you want to. And this will be my answer. Okay, so we like to multiply and divide these. Okay, we'll see if it carries over when we start doing powers and roots on these in the second half of this video. Before we do, I want you to try this. I want you to try the product and the quotient on this. See if you can match the answer that I get. And again, we're just taking this down to its polar form. And so don't worry about going any further. I think some problems in the book, they did go further. I'm not interested in that just yet. Go hit pause on the video, and then we'll see where we're at. Almost messed up. You almost got another video to start from the beginning. I don't know why I keep putting parentheses right there. You can put parentheses around it. Obviously, I'm not going to care. I do need parentheses around the cosine and sine part because this force, if you remember from the last video, the 4 squared to 3 actually distributes through. And so I almost messed up. I still had a minus sign right there. And so I'm glad I caught it. Let's just start all this back over. If I did still mess it up, let me know in a non-harsh manner and drop a comment underneath this video on Google Classroom. Well, when you raise it to a power, Demoivre got a little bit greedy. He says, okay, I've done all this work for you guys in order to be able to multiply and divide complex numbers, but when you raise it to a power, we're not going to call it like a power property or a power theorem. You're going to call it Demoivre's theorem, okay? And so if z is equal to a complex number that's in polar form, like so, then if I want to raise it to a power, good news, we're starting off the same, r to the n. And then on the inside right here, I'm going to take the n and multiply it by my theta. Whatever I do for one theta, get used to doing it for the other theta as well. Not real tough. It's just Demoivre just finally wanted something named after him. So great note card material. Again, formula sheet. Hey, your 3x5 poster board, whatever you're using as a cheat sheet on this next quiz or test, get this on there so you can refer to it quickly. You don't have to come back and find it in the videos or the notes. Okay? So now they made it a little bit harder on me. Right? They gave this to me in rectangular form. And so I've got a little bit of work to do before I get going. It's not bad. I need the review. And so I need to find my r and my theta. Okay, so remember my r is going to be the square root of 1 squared plus 1 squared. Real squared plus imaginary squared. So it's actually going to be the square root of 2 right there. And then my theta. Theta's not going to be too hard to find. I'm going up 1 and over 1. And so it's obviously 45 degrees. We can call it 45 degrees. We can call it pi over 4. We've done everything in degrees so far. Degrees would be easy on this, so let's go hard. Let's go pi over 4. Remember, you can also get that by x equals r cosine theta, or you can use y equals r sine theta. They both give you the same thing. X is going to be 1. Cosine theta is, x is going to be 1. R is going to be the square root of 2. There we go. Cosine theta. So yeah, cosine theta is equal to the square root of 2 over 2. we're definitely talking about a pi over 4 angle. Or 45 degrees. Work at 45 degrees and try to remind me, and I'll give you what that answer will be at the end. I'm going to work it with pi over 4. That just works better for me. Now, we didn't even answer the problem yet, because I want to raise this to the 5th power. So this complex number I found to the 5th power, according to Demoivre, it says to take whatever your r is, raise it to the 5th power, and then multiply, I know you could do this in your head, but multiply each of the angles by pi over 4, or by 5 as well. Now, a lot of you are just going to plug this in your calculator and you're going to get the right answer. All right? Square root of 2 to the 5th power. I'm going to show you what I do over here. I do square root of 2 to the 5th power. It means that the square root of 2 is going to be a factor of itself 5 times. So square root of 2 times square root of 2, well, that's 2. Square root of 2 times square root of 2, well, that's 2. This guy doesn't have anybody to play with. 2 times 2 is 4. And so that's what I want to see out here is this 4 square root of 2. I don't care if it comes from a calculator, if it comes from your head like that. Either way is fine. And the rest of this, I just kind of cruise with. Remember, this is actually 5 over 1. So if I do a numerator times numerator, and then a denominator times denominator, it gives me 5 pi over 4. So if you did use the 45 degrees up here, instead of the pi over 4, let's see, 5 pi over 4, that's 225 degrees what you would have got there. And you also would have had to use a calculator in order to find that. Here I just did 5 times 1. So thank you, Demoivre, coming up with that. Made it so high school students and teachers like me and you can figure this out. Okay. Last one, and it's just the opposite of what we just did. It's kind of like the opposite of the of Demoivre's theorem. It's called the nth root theorem. It's not as fun, all right? And so here we're going to be taking the nth root of a complex number. Now I know that's not an nth root. It's z to the 1. It's z to the 1 over n. But if you remember from algebra 2, that is the same as the nth root of z. Okay, so either way that you want to write it, it might be better to write it as an nth root of z. That might work better for us. And so in order to figure out what this is, we're going to take the nth root of r, or they might use r to the 1 over n. Okay, I think the book does use that. I like the nth root of r. And we will now multiply that by cosine of, well, think about it. We just multiplied our theta by n. So yeah, it makes sense to divide our theta by n. But we're going to have more than one answer. Just like whenever I take the square root of 4, I get plus or minus 2. When I take the square root of a z, or a third root of a z, I'm going to get 2, maybe even 3 answers. And so I need to tag on a 2k pi over n to the end of that. And as you've noticed, whatever cosine gets, sine gets as well. Some people call it 2 pi k, 2k pi. It doesn't matter. Over n. Both of these being over n is kind of the same idea we had when we had a multiple angle earlier. We had like cosine of 5 theta equals, I'm going to make up something, pi over 2. And so we found that 5 theta was equal to, I'm just coming up with stuff of my own right here, not pi over 2. I don't come up with my own stuff. Equals 1. No, I want to do 0. Cosine theta equals 0 at, there's where the pi over 2 comes in, I was thinking of. And at 3 pi over 2. Remember how I had to divide everything by 5, including the plus 2 in pi? In order to get theta equals pi over 10 plus 2/5 in pi. Same idea with this. How I divided both sides by 5 right there, I'm just dividing both sides by n. I'm making that look a lot harder than what it is. And it is tough to graph, but we're not going to go as far into graphing this as possible. What you need to know is that this k right here It just simply stands for an integer, starting at 0. It's just plugging in each integer until we get to n minus 1. I'm going to show you exactly what I was just talking about. Let's throw in some numbers because I am just rambling by now, and everything probably sounds way more confusing than what it should. Alright, I want to evaluate the cube roots. That says roots. So there's going to be more than one answer. I'll tell you how it says cube roots. There's going to be 3 answers to this. Of z equals this complex number. Okay, so according to my formula, what I want to do is I'm just going to first write out kind of a blanket as to what's going on. So I'm wanting to take the cube root of z. I'm wanting to take the cube root of that 8 out in front. And then I am going to, I should be writing smaller. We got a long way to go on this. I'm going to take the 2 pi over 3, divide it by 3. This guy right here is my n. Plus 2k pi over 3. We'll buff that out in a minute. Plus I sine, unless we get the same thing. I feel pretty confident in it. I'm going to just bring over everything that was on that side. So what does that mean? Well, let's simplify it real quick before we get going. I can take the cube root of 8, it's going to be 2. I'm going to simplify as much as I can so I have the least amount to plug in. All right, so 2 pi over 3 over 3, let's call that 2 pi over 9. Unfortunately, this 2k pi over 3 does not simplify. I mean, I could write it as 2/3 k pi, but that doesn't really get me anywhere. Plus I sine of the same thing. Okay. Like I said, there are going to be 3 answers on this because I'm taking cube roots of it. Yep. So, first off, I'd like to put a k equals 0 over here. 0 is the first thing I want to plug in for k. And so, to find out what my first cube root is, when I plug 0 in for k, that is going to give me 2. And then cosine of 2 pi over 9. Now, if I plug in 0 in for k, I'm going to go ahead and show you on this one. I'm going to overteach it just a little bit. But if I do 2 times 0 times pi divided by 3, that 0 wins out. And it makes it so everything in there goes to 0. So as you can see, most of the time, it doesn't really help to plug in 0. Right? It gives me a really good first root in the fact that all of these just cancel out and go away. And I'm just left with my first root of this complex number is 2 cosine 2 pi over 9 plus I sine of 2 pi over 9. So that's my first root on this. It has a second cube root as well. I find the second cube root by plugging in 1 in for k. So what does that give me? It gives me 2 times cosine 2 pi over 9 plus, well, this time it's going to be, if I plug in a 1 right there, it's going to be 2 times 1. Let me go ahead and show that 1 right there. I think I'm going to lose you guys on this. There's a lot going on. So that'd just be 2 pi over 3 plus I sine the same thing. 2 pi over 9 plus, over here I'm just going to put 2 pi over 3. It's still 2 times 1 pi over 3. And so I just have the cleanup on this. The cleanup on this is going to be adding together these two things. And so I'm really running short on room on this. So I'm going to write something down and then erase it. In order to add these fractions, they have to have a common denominator. So I have 2 pi over 9 plus, I'm going to need this to be over 9 as well. So if I multiply this by 3, I need to multiply the 2 pi on top by 3 as well. So it gives me 6 pi. Just looking at this 6 pi over 9 right here, that is still the same. 6 over 9 is the same as 2/3. I just rewrote it so that I can add these fractions together. 2 pi plus 6 pi is 8 pi. And they're both over 9. And the good news is, once I do it once, I'm going to get the same angle in both the cosine and the sine, the real and the imaginary part. If you're struggling on this part right here, I'm going to erase it real quick, and I'm going to redo it again, because I have one more to find. I'm supposed to have 3 answers on this one. So let's go back to red. We're going to go k equals 2 on this. All right? If k equals 2, that is going to give me 2 cosine of 2 pi over 9 plus 2 times 2 pi over 3. Well, we know that's going to be 4 pi over 3, right? So whenever I do the sine part of this, I'm going to call it 4 pi over 3. Okay? And I'm going to want that cleaned up into a polar form. 2 cosine, let's see, we have 2 pi over 9 plus, well, that's, let me add this side over here. I have 2 pi over 9 plus, well, if this is going to be over 9, again, I have to multiply that denominator by 3. So I multiply the top by 3. 4 times 3 gives me 12 pi over 9. So that would be 14 pi over 9. And that would be my angle. So, after all of these easier formulas, this is still way easier than what they used to have to do. But I end up getting these 3 answers. And you're just going to have to practice this, guys, as far as getting those 3 answers. This is not easy. We would have had some activities in class to do over this, but I assigned some in the practice problems for you to do. Okay? Before you get to there, though, if you have questions, make sure you have them ready for the Q&A, and I'm willing to bet that you will. I want you to go ahead and find the 4 fourth roots of this equation, of this complex. Hey, before we do that, though, let's talk about that. If I'm doing the nth root of z, let me give you a formula for if we have it in degrees, right? I think that you would be able to make sense of this, but I'm still going to take my theta and divide it by n, but this time instead of adding 2 pi, I can just simply add 360k over here. So I just simply exchange my 2 pi in my formula to a 360. Or you can easily change this to 2 pi over 3 and work it out. Whichever one you feel comfortable with, go with it. I'm going to work it with the 120 and use the 360 in my formula. Okay? So hit pause on the video. I'm going to try to fit it all on this screen, and then you try to fit it all on your paper. Did you find any shortcuts in working these? Well, you can go ahead and do this 360 divided by 4 right here and just call it 90. That made it a lot easier to plug in if you saw that. So all these in degrees will go a lot better than the ones that are in radians. And so I tried to show my work here, plugging everything in. I've got my 4 answers. And something I didn't mention earlier, notice that I stopped at k equals 3. I always stop 1 less than what my n is equal to. So I'm taking 4th roots right here. I stop I do not go to k equals 4 in this case because that would end up cycling back around and should give me the same thing that I got right here, just a coterminal angle. And so 4 answers on this one. Practice, practice, practice this stuff, guys. We are getting in the thick of it right now. And so hope you see a need to practice this. These are the ones that I thought would be good to practice. I'll try to model the quiz after these type of problems. If you have any questions on this, have them ready for the Q&A. See you guys later.